Right. Welcome, everybody. Happy New Year. Tonight, our speaker is Dr. James Johnson. He has worked on all manner of optics from one.
Can you pitch the next talk first?
Yeah. Do you want to pitch it?
Sure. Give me 1 second. I gotta find a screenshot of it. Yeah, sure. So the talk on the next talk on February 20th. This is all on the website, including the abstract. It's going to be a professor from Tufts, and the title of her talk is "Ethical Photonic Integrated Circuits from Neuroscience to Quantum Applications." Her name is Professor Seema Mohanty, and probably used to them in continuing engineering school. And that'll be February 20th. And the abstract is on our website.
Is that the third Thursday?
Yes, I believe so. So, okay, shoot.
Thank you, David. So, again, our speaker is Dr. James Johnson. He has worked on all manner of optics from 1 millimeter to 8.4 meters in size. He is a technical staff member at MIT Lincoln Lab in the optical engineering group. He holds a BS from Purdue University in applied physics and a MS and PhD from the University of Arizona's College of Optical Sciences, where he helped with the fabrication of the first giant Magellan telescope near and Rubin Observatory's primary/tertiary monolith. His current work focuses on novel optical designs in the UV long-wave infrared, the freeform optical systems, and advanced metrology. Prior to joining MIT Lincoln Lab, he worked at UTC Aerospace Systems, developing high-altitude ISR cameras. He holds 7 U.S. patents, more than a dozen peer-reviewed published papers and proceedings, and is a member of Optica and a senior member of SPIE. Welcome.
Thank you all so much for having me. I'm really excited to be here to get to talk about a lot of the development that the lab has been doing over the last decade in freeform optical design, kind of our special methodology that has been developed and is in use here, and a lot of the advancements that we've made in just the last couple of years with our system. So those of you who are familiar, it's not updating. Well, that's unfortunate. Let's try this again. So, where's the clicker? Oh, okay. Well, let's do that. I'll just make it on my side and then take over here. Okay. So those of you who aren't familiar, MIT Lincoln Lab, we're part of MIT. We do a variety of missions. The core 3 missions, though, of Lincoln Lab are systems architecture, long-term technology development, and complex system prototyping. And I really want to focus on the prototyping because the prototyping is what the engineering division, which is where the optical engineering group here at MIT Lincoln Lab sits, is our core function to design and develop next generation advanced prototypes. And this is all manner of technology. In case of the optical engineering group, that really focuses on novel architectures for optical systems across there. Okay. Still not clicking. Okay. No, I can't see it on my screen. So, we see a lot of applications for free space optical systems. And really, this is, freeform application in the free space area. You've got your classic defense, within Earth or ISR type capabilities, targeting fire control. But then you get the dual use in civilian type space, laser communication. That's a really hot area right now. Being able to create high-speed data links over really, really long distances. MIT Lincoln Lab is really proud about that area specifically since we developed some of the highest performing terminals in the world out of our facility just down the road. But also, your remote sensing, your hyperspectral monitoring, and persistent awareness, both in that civil area where you want to be able to monitor facilities on the ground, as well as other sorts of assets. So, we're going to kind of go over what freeform optics are as part of this talk. the way Lincoln approaches freeforms that varies from how many other places do, especially in the commercial space and what's available in commercial code. And looking at how we have developed the tools to work this way to look at both imaging and non-imaging type systems. So freeform are surfaces without axes of symmetry. And I want to be careful with where I say it. It's not axes of symmetry, it's axes of rotational symmetry. You can have systems that are bilaterally symmetric, just kind of like your face, it's right, left side, but there is contours in the other axis. That would be considered a freeform. The beauty about freeforms are it lets us bend the mirrors to better optimize aberrations and increase performance. Just similar how you've got your bending factor for a normal lens where you can have the same sort of curvature, but you can bend the two surfaces to achieve different sort of aberration correction for the power on the lens, right? You can have the same focal length lens with different sort of curvatures by bending the two surfaces. We can essentially bend the surfaces, in locally using different sorts of equations, and that gives us a better chance to correct generally off-axis aberrations in systems. And this lets us push various levels of performance. Usually you're chasing something system, better resolution, bigger field of view. Maybe you want to shrink your system down and you can't control the aberrations. The smaller and smaller you shrink the system, being able to access those higher order terms for bending mirrors really lets us drive to an increased degree of performance in the system.
I understand your graphs. Isn't you just saying with the diffraction limit originally?
Sure. So you have the idea that you're mixing pixel size, essentially how small your detector is, and F number. So you think of your, spot size on that detector, where it really falls in the diffraction limit, and where you can optimize the system at a certain F number speed versus where it would sit with the pixel size that's there. You can see different flavors of this based on performances. If you've seen some of the papers Ron Driggers has generated about F number versus, essentially your range seeing capability. These kind of fall into the same sort of space where you're limited by your detector size on one side and how fast you can cram and the aberrations you can reasonably correct with a certain number of turns. And at some point, conventional optics just can't correct enough aberrations over either a given field of view or a spot size for a certain F number. And these are assuming you're maintaining some level of fixed term in one of these many parameter spaces that you can be chasing.
Why is the diffraction limit not just the one? It's kind of confusing.
I mean, you have a band, right? I mean, we consider diffraction limit things to be around, if you're thinking Strel ratio, it's 0.87, right? Anything that's, got a Strel ratio faster than roughly 0.87 is quote unquote diffraction limited. So it does have a sort of a banding in there, and there is a slight play in that space for, it doesn't have to have all of the conventional rays to be, exactly on the same spot. You've got some sweep in that region before your image degrades.
So are those lines around the two lines that define the diffraction limited area, are they based on the upper and lower bound of the wavelength band of the?
More or less.
Okay.
Yeah.
So then would I be correct in saying, if I take some basic equation for a diffraction limit, then I consider something like an IFOV in this case to review, take that ratio, that F number out, I could plot it similarly.
Somewhat similarly, yes. So getting to the point of using freeforms, requires solving three big challenges. The first is, and I won't put these in any specific order because they all have to be solved simultaneously to produce a freeform object. But I'll start with the design because that's usually the first thing that gets done in an optical system anyways, right? You need a way of describing what a freeform is. You need a way of translating that into the computer code to actually optimize it. There are too many parameters to do this by hand. And you then need a way to be able to take that design and actually translate it out to something that's usable by the fabrication tool, right? You've got to take those surface shapes. These are, you've lost all your symmetry, so your equations get a little messy here. And now you have to be able to have a machine that can actually create those shapes. So you need to add axes, you need to add encoders, you need to be able to add precision to your tool motion and have it, pathing in the tool motion and know where the pathing is, both in pressure, in stroke speed, all of the fun things you learn working in a polishing shop. When you do it by hand, now be able to do it over a computer numerically controlled system. Great, we've got 5-axis machines, we've got 6-axis machines. You could buy 8-axis machines if you want to. Great, we can now fabricate really crazy shapes. You still have to be able to measure them because you have to take those measurements of the surface and then feed it back into the machine. And once you fed it back in the machine, you know you actually did it right. And then you have to be able to put together your optical system. So if you don't have the metrology that can handle a surface shape that's not rotationally symmetric, one that you can't put on air bearing, you still have a problem of you can't put it together. So get to the point of being able to work with freeforms, you have to solve all three of these problems. And in the last, 10, 15 years, we've really gotten to the point where these are becoming solvable issues. Yes, freeforms have been out there. You can find patents of them out and back in the 80s, but it was very hard to fabricate and very, very hard to align, except in really small, limited use cases. We'll flash through this really quickly. This is kind of how it goes, right? You've got Newton back in 1700s, great. You get to the parabola, beautiful, perfect spot. Even Newton really didn't have great parabolic telescopes. They were hard to manufacture, right? It took several hundred years to be able to manufacture good parabolas, good conics, good ellipses. And then the 80s, great, we've got computers now that are doing stuff fast enough, we can start having them drive machines. It means we can start adding more terms, the optimizers can get better. You've gone from a couple parameters with a kind of constant radius curvature. Now you've got 10 or so parameters per surface. Well, computers now, they're so much better, we can start adding as many parameters as we want, within the limits of, whatever the latest Intel CPU is. And that means we can start having hundreds of open parameters running on the surface to bend and change and shape the mirrors, which means we need equations that can accommodate many, many more terms that are there. So A-spheres, I won't spend too long on this. The idea that you've got your core conic equation, your radius curvature, your semi-diameters, and a function that we think of as the base conic, and then we start adding higher and harder perturbations to the surface, which adds just a little bit of localized bending. It does become a little degenerative in these descriptions, which is why, things like NURBS polynomials, the Q polynomials have come about, and that you don't have terms that start fighting each other while you're optimizing. You don't want to be increasing this number and then finding you have to be tweaking other numbers. It does add some simplicity to the optimization method. And then we get back into the idea of freeforms. Now, what a freeform is a little bit contentious. You can ask many people and you get different answers on what exactly constitutes a freeform. There's really two definitions you can just select down. And the first is there's no axis of rotational symmetry. That one nobody will disagree with. There's a softer definition. I call it a softer definition because you can argue one way or the other. And that is parts that don't have any local axis of rotational symmetry. I personally argue things like off-axis parabolas that are made without a parent. Instead of making a giant 4-meter off-axis parabola and then coring it out together, you just make it as one little 12-inch off-axis parabola. Everything about making that off-axis parabola as a child on its own uses the exact same processes, tools, math that a freeform does. It's essentially a freeform, altogether that's there. And we got many different ways of describing it. You've got your polynomials. You can describe it purely in terms of point clouds. And then this way that Lincoln really works with splines and NURBS. So what is really the difference between point clouds? And I'm lumping NURBS and splines in with point clouds and polynomials. Polynomials are essentially, it's an analytic equation. It's a solvable analytic equation. If you enter in an XY coordinate on your mirror, you get a set. This is great, but that means that when you're optimizing, if you change one term on the mirror, the entire surface shape changes. So at some point, you get so many terms there, when you open up to more complex surface shapes, that small changes means your entire surface forms. And now the optimizer actually starts fighting against itself because it wants the mirror to be in position A, but it needs a little more correction in this one small spot over here. And to get it, it has to tweak the entire equation to bring that point down and keep the same spot there. The nice thing is if it's a fairly mild surface, you only need a couple of terms. You can do the job very simply. And with everything being orthogonal, makes everything very easy to describe. You've got a center point on the mirror. You can define your equation from that center point and everything works. Coordinate transforms can be very easy. And describing that overall shape when you're done, you can put a drawing, it's easy to put it in terms that manufacturing and metrology can understand. Point clouds are a completely different beast. And this is the where Lincoln really works, is the idea that instead of changing the entire surface shape, let's just change the localized points. Let's lay a grid down on the surface, describe that, find a way of describing the points in between the main control points that are on the surface, and push and pull up and down locally on it. Keeping the surface continuous, which means it has to be second order differentiable. We have to keep it smooth. We don't tend to like jaggedy optics. And this really works well for really fast surfaces where we want steeper curvatures, really fast compact systems. The other nice thing is that we can use different sets. We're not limited by the number of polynomial terms we include. With polynomials, you have an expansion. You got to keep going. If you want more correction, you have to add more terms. Not all of these terms are even useful. In fact, if you're using newer versions of Code 5, they've learned that, yeah, if you've got certain symmetric systems, you just shut off half the terms that are there because they're controlling aberrations that don't exist in certain types of systems. You have to cherry pick. You have to really know what equations you're working with. Point clouds, we're going to brute force this. Brute force this. We're throwing out the equations. It's just pushing and pulling on those points and then redefining where they are based on some arbitrary point in the system. That means we can get to the exact most optimal surface shape. There is no limitation in the computer code other than the bit resolution you're working with for what shape that can take and how well your optimizer can go.
Don't you still interpolate between the points?
You do, and we'll get into that in a little bit. And that's actually one of the biggest risks of this is how well that interpolation goes. What that resolution is between the points, how well, because this has to be numerically calculated, which means you have to understand where the ray intercepts the surface and how precisely the algorithm can get back to it. This is where NURBS really works well because there is a analytic equation that can be solved, and there are many, many, many really beautiful solvers out there. It's the basis of all CAD software these days. So they know how to make it work very accurately in most modern computer systems. I have an idea for NURBS for people who haven't really thought much about NURBS. They came out of essentially shipbuilding, right? If you want to build a curved hull, you take a piece of wood, you slap it against two really strong spars, and you essentially start bending the wood around it. How do you describe that shape? Well, shipwrights had to come up with methods to essentially create these unique curves that don't have an equation tied to it. And NURBS are described, mathematically, they ended up being described by French automotive engineers who wanted to start making prettier autobodies for their cars. Great idea, and thanks to the people at Renault and Peugeot. But NURBS are ultimately described by three things. You've got control points, where you lay out your grid, what we call knot vectors. So essentially, you take a string directly down from that control point to the normal point on the line, and then you start pulling. And you can do this with a violin string, and you can create all kinds of crazy curvatures by just tying a knot to that string and then pulling on it to get the different sort of curvatures. And based on the number of points and how hard you pull, you can create all of your shapes that you want. The last thing that's important is this idea of order. It's shown as degree here. And the idea of order is how many adjacent control points control the curvature of the system, right? If it's just one point controlling it, you're going to get a very jaggedy, you get discontinuous surfaces. And NURBS can actually describe discontinuous surfaces, right? They can describe, polygon type shapes if you wanted them to with order 1. But when you start adding degrees, now the adjacent points matter and you start getting nice smooth curves being driven through. So the higher your degree, the more the adjacent points begin to matter in the system. And that becomes a big factor with NURBS optimization for raytracing. Ultimately NURBS describe every shape. It's not limited by terms, it's just limited by point cloud density. So, we can get to really, really, really fancy shapes just by manipulating a certain set of properties and do it faster in many ways than where polynomials can for complex systems. So back a little over a decade now, Michael Crisp, who was still is a senior staff member here at the lab, recently mostly retired, developed a method for describing NURBS-based optimization called FANO. And you'll hear this a lot. The acronym FANO doesn't really matter. I think it changes every couple of years when somebody else can't remember what it stands for and comes something new. So don't worry about so much about what it means. It's just FANO. And what FANO is it's a way of taking an optical system, converting all of the surface shapes to NURBS in kind of a internal global coordinate frame, and uniquely ray tracing. It's a full ray tracing engine, custom designed to then optimize the ideal surface shapes that are in there. We've spent a couple of years developing a direct GUI connection to Zemax. So we can open it up, it'll take a Zemax file, it'll convert it over into the FANO language, spit out a FANO design file that we can then optimize against and iterate in different parameter sets to try and get truly the best shape possible. Then we can actually take it and feed it back in to Zemax Code 5 to do all of the analysis. That's the nice thing about the API, is that we don't have to build any of the analysis tools in FANO. They already exist in Zemax. Why are we gonna, redo what's there? Ultimately, what we've learned though is that FANO is really a fantastic last mile solver. And what I mean by that is it doesn't get there from the jump. You can't just hand it, a flat surface and it'll create the world's best telescope. You got to get it close. You have to do 90% of the work to get it where you want it to be, and then let FANO run. And then FANO will take it all the way down to the peak performance that it can.
Can Zeno ray trace a NURBS surface? I mean, doesn't it need a polynomial to
You can enter it as what they call a grid sag surface. So you can put in and Zemax can trace a third order spline. So it's not a true NURBS. NURBS lets us do some shifting of the points. So FANO will actually re-register and reinterpolate the points back to something that a third order spline will be able to correctly attribute the surface. So Lincoln was kind enough a few years back to actually create a video of the FANO process. Let's see, one just here. The idea being you can keep it somewhat real time. You've got your surface, and this is starting flat. We barely ever start true flats. So your image plane up here with a variety of rays looking at the control points and the FANO solver, and then FANO goes in, it kind of iterates around, figures out how each of those control points influences the rays, and then it starts looking at how does it minimize their overall RMS spot size in a sort of direct way where you can see how each control point then influences the overall control function for optimization.
I have a question. Is the software optimizing like the grid density, or is that something that's defined by the user prior to the analysis?
It's very much defined by the user prior to the analysis. And it's part of the art of working with the software, that you have to have a density on the surface. You have to at least know where you're starting. Because NURBS, where your control point is defined both locally and how hard it's pulling, you just at least give it a basis to start working with. And adding points, it's easier to do manually than
Is it always a uniform grid, or do you do non-uniform?
You can do non-uniform. There are different user settings that we can make while we're going through the optimization. Uniform grid actually tends to work pretty well. So technically it is a third order spline when the grid is uniform. So at least from experience, it's worked pretty well. There are a couple cases where the non-uniformity can help. So with that, Michael developed we call it the Freeform demonstrator, which you can see right there. This is his original design to show the power of freeform surfaces, and particularly the NURBS surfaces. So this is not looking at Zernicke's or XY polynomials. This is looking at how NURBS do compared to A-spheres. You've got, this is an f2 telescope with a 6 degree by 6 degree square field of view. The conventional aspheric terms out to the 14th order give about a 28, 30 micron-ish spot size in the visible. You convert all of those surfaces over to NURBS. You know, you can see the different sampling grids there. You know, primary is a little more densely sampled than the secondary. Same with the tertiary. You know, you get an almost 6x reduction in your spot size. Same telescope volume, virtually, I mean, a little bit different, but essentially same telescope size, same, at least first order performance, big increase in optical performance.
But my question becomes, but how many parameters do you end up with to do something like that? Or you're
23 squared by 19 squared by 29 squared. Yep. They're all multiplied together, and then you've got your ray functions that also come in, and we'll get into some of that. Right, each of these might have 26 terms total for a Zernicke, or if it's A-sphere, 10 terms each, right? We've got several orders more terms running, but computers are so powerful these days. What's a couple thousand parameters open if you've got, computers that, your iPhone's more powerful than the space or the space shuttle was, right? It's nothing.
So one of the something about what it's like to align this and actually assemble this.
I will get to that at this.
Totally told me that it's useful, but now I'm anticipating that it's much more difficult to really.
I will definitely I'm going to make sure I save time for those, because that's actually some of the most interesting stuff we've been doing the last few years. Demonstrator, as I say, you can see it up there. Most of this is aluminum nickel plated mirrors and aluminum housing. And how well does it really do? Well, we could take it up to the roof of the building and start imaging stuff. That's a water tower about, we think it's about 6 miles away. It's hard to really tell, but it's about 6 miles away from the roof of the building. You're seeing about 27-ish microrad of IFOV. And that water tower, which is 40 feet tall, you can see exquisite resolution. You can see the whip antennas coming off the top of it, which are very hard to pick up. Things like the water feed line there. Because we know what the point spread function is of the all aspheric design, we can actually backfeed it into the model and devolve the image, because we know how the point spread function changes. And you can actually see the dramatic difference. Water tower, that's a building. It might be a grain. I'm from the Midwest. I would think it's a grain silo if you showed it to me, but you can't see any detail other than there's a building there. It's amazing how much better it really does. So working with Phano, we're gonna, it's kind of the parameters. Phano's kind of a unique beast to work with. There are a couple strong rules we've developed over the years that you really have to be aware of when you're thinking about designing systems in there. First is that, a lot of parameters are hard to trace. So right now, Phano is at least enforcing bilateral symmetry. So that means, you've got to have a parity left to right. And that means we only have to trace half the rays, right? If it's symmetric left to right, you just say the NURBS surface is going to be the same on the left side as the right side, and you just worry about the 1/2 that's there. You've got this issue of ray aiming. This is a problem with every commercial code, right? They always struggle if your stop is buried in the back. Code 5 and CMAX deal with it different ways. We have kind of the same problem, because it's homebrew code. We can't really deal with some of the complexities. So we need an entrance pupil somewhere directly we can fire into to make it work. That does kind of limit some of the systems we can do, but even this one, the secondaries at the stop. So we've got tricks we can play to force that entrance pupil out to the front of the system. Nyquist sampling and boundary conditions are really the key of working with Phano, figuring out how to solve Nyquist sampling, make sure you have 2n+1 rays for every control point in the system, and how you handle the edge of your NURBS grid. I want to cover into that a little bit. Nyquist sampling, this is a challenge, right? I mean, when we're doing normal ray tracing, we want to trace as few rays as possible. You might trace just your reference rays on the outside and you've got ray down the system. You might trace a couple rays coming up in field points, But the problem is with NURBS, if you don't have a ray on a control point, the NURB doesn't know what to do. It wants to stay continuous. And so it leads to this massive swing and ring because there's no ray here to tell this point that it really needs to be up on the blue curve. So it's going to just sit wherever it wants, where it thinks a third or a fifth order NURB spline wants to be. It will hit exactly where a ray strikes though, right? We've got exact representation at the 3 points it does strike. Great. This is true, and this is very much, in the case of when we're talking about optics near pupils, right? We've got the full ray grid, it's all covered, all the field points are hitting the same. We tend to get really bad fit if you heavily undersample the systems as we would with normal conventional symmetric optics. So, first off, you need to, you have to heavily sample. You've got to fire a lot of rays. So it's not just having a lot of open parameters, you also have to be tracing a lot of rays in the system. You want to make sure you've got at least 2 rays plus 1 for every point, and now you get a much, much better fit, right? You still, the moment you're off the grid, it's going to start ringing, but hey, this is what we care about. So we've got a good optimization here. The challenge is, though, there's also field optics, right? There are optics that aren't per pupils, and that means that your rays, if we'd like to trace as few field points as we need to optimize the system, they tend to squish down, and now you run into the same problem where on your field optic, you've only got a cluster of rays governing a single control point, and you've got uncontrolled field points now, or I'm sorry, uncontrolled control points that don't have any field rays tied into them, and you end up with the same sort of discontinuous effect that's there. So you have to oversample the field to make sure that you've got 2n+1 field points per control point at those surfaces. So you have to really know what's going on in your system, which optics are at field, essentially intermediate images, which ones are at pupils, and which ones are the in-between, and figure out how to balance enough field points to pupil rays in the system. This essentially leads to a quartic growth in the number of rays you have to essentially chase within Phano. So we're tracing a lot of open parameters, we're tracing a lot of rays. It can take a little while, but when it lands on a solution, it's going to be better than anything else that's out there. I also want to mention boundary conditions, right? Your mirror has a finite size. Your clear aperture cuts off somewhere. Your mirror, no mirror runs to infinity. So we tend to like to trace rays out to the edge of our clear aperture. Great. But again, you run into this ringing effect that's there when you're past that clear aperture. The other thing is, remember, all of your NURBS points with orders higher than 1 rely on the adjacent points to define the shape, right? The adjacent points are also pushing and pulling on that shape, which means that if you have a control point outside of there, it's going to be affecting the control point that you do want to be working with. So you run into this fact that you start seeing, ringing, you start seeing edge ripple, you start seeing bad fits right at the edge of your clear aperture because you don't have rays at that next adjacent control point to tell, hey, that next control point, I need you here so that the control point I really do care about is in the right position. It's one of the limitations of working with NURBS that, that the system works on the whole, and you have to understand that sort of interplay between, adjacent, local optimization points that are in there. We spend a lot of time actually, this is where the art really is. It's figuring out how to balance, a lot of these different parameters and understanding that you have to extend how far you have to trace. We have to oversize the system. We have to trace bigger pupils. We have to trace bigger fields. That way we make sure we have rays outside of the control points to control the control points that do lie outside of the mirror, but we want to be able to then achieve much, much better fits to the ideal surface at the point. And then we can just slab the mirror to where we want it, right? Those control points don't exist in the real world because they're outside the clear aperture. So we can optimize to it and then just cut it to where it needs to be. All right. So, now we're going to get into kind of the practical bit. We've done imaging systems, but I personally am really interested in afocal systems. We, got a variety of parameters we're very used to chasing when we optimize, generally spot size or wavefront error. We also tend to have a fixed focal length or field of view that you're working with there. Afocal works a little differently. You're chasing collimation. You want to have the flattest wavefront you possibly can for a given field point. And, you know, there's always usually a magnification factor that's in there too. You know, how big or how small you're making it, how much your angular distribution on the input versus output will be. There's a secondary target you tend to chase in afocal systems, and that is exit pupil. You know, in a lot of cases, you want a physical accessible exit pupil or physical accessible entrance pupil in the system. This be exit pupil because interesting things get put behind the exit pupils. The basic first order equations. The real advantage here, and remember, Lincoln is interested in prototypes. We want to build prototypes. With an afocal system, to create an image, you just put an imaging lens at that exit pupil to your camera. But that means now you need a prototype system this big to get access to an aperture this big, right? You don't have to build a system that is giant to be able to prototype it anymore. If you have a common afocal design with a really nice, well-controlled exit pupil, you could do a lot of really interesting development work and gain advantages of those sort of bigger systems. However, teaching Fano to go from imaging to non-imaging, that took us a little bit of time to really lock down. The solution proved really simple, but it wasn't really straightforward. We had to work with Michael for a good 6 months to come up with this. You know, Fano, like most software, chases spot. Your X, Y, Z in a given spot. You don't usually worry about Z because it's on an image plane. They all tend to, if it's a flat image plane, they all tend to have the same Z value. So really it's just trying to minimize your RMS value for a given. But all ray tracing software also tracks what we call direction cosines. These are the angles effectively that the rays are moving through the system, right? To be able to trace a ray, you need both its position and its angle that it's moving, and then the distance it's going to hop to the next move. So we can look in terms of direction cosines, which the Ray optimizer is already tracking. It's part of the Ray database, and you can pull this down from the 5 database, and ZMAX also has this in their optimizers for people to view. And then we can just take that same equation, replace the terms like from linear to angular, and then try to minimize that RMS column. And this is functional with ZMAX and 5 in their engines when you flip on through afocal mode or whatever the afocal system really, description there. So we managed to convert the engine to be able to let us switch between imaging and afocal to start doing more of these prototyping, universalish sort of concepts. And that's where we get to building our next gen freeform telescope, which sadly I couldn't bring today, but we wanted to be able to show what we could do in this sort of afocal space. So we were set out with a concept task to see if we could come up with a plus or minus 2 degree field of view system. So 4 degree circular field of view telescope with a 6-inch, 150 millimeter entrance pupil and a 6x magnification. And how low a wavefront could we possibly achieve using our sort of NURBS shade? So we had a notional volume we wanted to be in and a notional weight we want to target, but really, again, accessible exit pupil. Can we get it to go from 150 down to roughly 1 inch in the back? And maintain a really large field of view. Remember, most afocal systems are plus or minus half degree. They won't even stay really diffraction limited above. You can get them to 1 degree, but they're not really high performance out of that plus or minus 1 degree. So really, how far can we push it and maintain really exquisite performance? There you go. Yeah. So remember, Fano is a last mile solver, so we have to get an initial design. It's not going to know what to do. Personally, I'm very interested in these ideas of folded TMAs. TMAs, so 3 mirror anastigmats, where you've got primary, a secondary, and a tertiary mirror, but you fold it so that it makes this volume more compact because you're essentially running the rays inside the space that's in there. This has been done. There are designs out there. There are legacy telescopes that are running with this sort of design concept. Search all through the literature and find various concepts out there. But one of the beauties are you get this nice accessible exit pupil. You can even, if you do it very carefully, though it's hard with systems this fast to get an intermediate image that's accessible, so you can do a really nice field stop cut down straight light. Doesn't always work when you're going for compact, but it's there. You'll notice though that the all A-sphere design, it's really hard for this sort of field of view, this magnification, this entrance pupil size, to get below about 0.2 of a wave RMS at 1550. So we got to do better. Let's go to Zernike's. We can take that design, we can add Zernike's to all of those A-spheres, we can go back in, we can re-optimize, select code 5, let Zemax just churn, try to find a really great solution. It's a lot better. It's about, it's good 5 times better than what the all A-sphere design was. We've got a couple high lobes through there, but it's really not getting down to that. Like ideally, we want to be starting around 50th wave. So when we start building a system, it's going to be fairly low performance. So we can convert that now to NURBS, and you can see the difference. I'm going to flip between these two slides here so you can really see these are on the same scale, right? You can see how much less wavefront error there is across the system. It still has that folded TMA appearance. The mirrors have not shifted dramatically from more or less where they started, but now we're talking half the performance of what the Zernike was across the field of view. And this is less than a 50th wave over 97% of the field of view that we're talking about. That's the residual, right? That's where we're starting, but that's where we're starting. So that gives us a lot more buffer to be working with. We have a lot more room to work with when it comes to tolerancing and aligning and building. And there are a couple papers out there that the lab has published where we talk about, the benefits of NURBS versus Zernike versus just A-sphere. We do tend to find that freeforms are less sensitive than A-spheres are to general mode. General comparison, a little more here. I like to have the RMS histogram up because you really can see like the distribution of where all of the the peaks and valleys and how low the NURBS performance is with regard to RMS. It's RMS wavefront error. It's RMS collimation. This is analyzing Zemax at this point, so it's really RMS wavefront error. You can see that the histogram has really moved into about 0.01 waves over more than one sigma distribution on that plot. It is vastly better than Zernike's for systems that get modestly to, highly complex. So now we've got our design. We've got to figure out how we're going to actually make it because our sponsor's like, no, we want you to go and actually build and prototype it. Great. We want to build prototypes. That's what we want to do. So, this is where myself and Chris Roll, who's in the audience here, sat down to figure out how we take a really, really beautiful NURBS point cloud design and make it something real. You got problems, right? We can't do a lot of in-house code. This is a small rapid prototype program. So, we've got to think about how we get the shapes into CAD, how do we spread them in CAD, how do we get the prescription then to line up to datum sub mirrors, how do we get them to translate so that we can convert it to MRF codes, or not both MRF code and diamond turning codes, so that the machine knows how to make shapes. Since we're not talking about polynomials, these aren't embedded descriptors in the normal CAM software that the machines are making. And then, of course, same problem getting into the metrology, how do we do it for metrology? The biggest challenge, I will say, the biggest challenge with freeforms, coordinate frames. I will harp on this. I will harp on this the rest of the night. Coordinate frames. They are the hardest thing we deal with. Chris and I have spent so many hours in meetings discussing where on earth the coordinate frames sit, because the mirrors are all in local coordinate frames. They don't care about global datums. To build a system, though, you need a global datum somewhere. You have to say this is the truth, and the local coordinate frames also where the surface is, not where the mirror is, like the physical mirror is. So coordinate frames become a real hassle, and a lot of time is spent developing ways of describing them and making sure that then they translate and travel properly, and you don't lose fidelity as you have to switch from one global coordinate frame or one local coordinate frame to another local coordinate frame, right? Every time you interpolate, you risk degrading the quality of your system. So, Chris did a fabulous job with this optomechanical design. We've got our mirrors, the aluminum with nickel plated surfaces, our, sort of contoured housing that we came up with. And then started thinking about how do we do this right? Part of this is working with freeforms, you need to have a lot of really good fiducials. You can never have enough fiducials in your system. If you want to measure something, it's got to be put in before it's actually manufactured. So if you do too many, not a problem. You probably won't use it, but fine. But if you really end up needing something, you don't want to end up needing it after it's made and you can't have it. So the mirrors all have precision clocking features. They've got precision mounting points. We have places where we can manipulate each one in 6 degrees of freedom. We also include features like pockets in the back of the mirror where we can mount SMRs so that we can see relative to a CMM or a laser tracker where the mirrors sit. We also take advantage of another technology that was developed at the lab, something called the arc mount, the adjustable relocking ruggedized kinematic actuator. This is a little piece of technology developed at the lab 3 or 4 years back that is a vibration and sag insensitive actuator. It has a way of us to quickly unlatch the system and be able to turn it like a normal Newport or Thorlabs, Matoyo type actuator system to make very precision measurements. And then we can engage the locking mechanism, which will hold more than 20 G RMS of vibration load. That means that we can send it to a shaker, shake the heck out of the thing, put it right back on the optical table, and it's in the exact same position it left. And that means we don't have to hard shim anything. That makes the job so much easier because now you can make a lot of rapid, quick iterations and know that it is insensitive to even somebody actually bumping the table that's there. In this case, we've used them all in tip tilt locations, opting for more manual positioners for centration and clocking, but we can loosen it, make those adjustments, crunch again there, take measurements, and go. Everything was fabbed in-house, except for the 3D printed housing. Mirrors start off rough, they go into diamond turning, then they get, essentially iterated on over there in our diamond turning facility. Again, data interpolation, big issue, right? How do you translate the point clouds from the NURBS space to the CAD space, which is also NURBS, but you want to make sure that it's got the exact same formatting in SolidWorks that it did in ZMax, and then make it over to CAM software so that DiffSys or whatever tool you're using to program your diamond turning machine is following the exact same tool path needed to recreate that surface, right? These are non-rotational symmetric surfaces, and it's spinning the part along a spindle axis. You got to make sure things are really, really right, especially over repeated cuts to further refine the surface. Coordinate frames, it's all really comes back again to coordinate frames. And of course, we have the usual issues of mount-induced error, getting on the chuck, making sure the surface doesn't bend. A lot of the fiddly things that come with any sort of high precision polishing or manufacturing of optics. Of course, same thing with metrology. We are very, very fortunate to have access to a LuFoScan non-contact profilometer. This makes the job a lot easier because we can take our point cloud, feed it into the system, and be able to then take fairly high resolution images of the surface to get the figure to the resolutions we want to see. So we can see the mid-spatial ripple, we can see the cutting errors, and then feed that back into the diamond turning machine, iterate until we get to the sort of performance we want. Ultimately, we did send the mirrors out to be MRF'd so that we could really refine the performance down where we want beyond what the diamond turning machine could achieve. But still, it gives us an idea of being able to quickly iterate on and then verify once it got back from MRF, how well the mirrors work. Once they're done, they go up on the CMM, they get measured against our laser tracker. That way we know because our housing's got laser tracker fiducials all over it. The mirrors have laser tracking SMRs all over it. That means we can position the mirrors to the housing within about 25 microns of ideal position. And that's a great starting point. That's a fantastic starting point. So then we have to put the system together and align it. The question was earlier, how do you align it? Well, this is really where the challenge is. When you think of alignment, it's a sequential process. You start with your housing, you get it all nicely lined up. You put your primary in, you do all your metrology, get your primary lined up. Then you put the next mirror in. You have all your metrology set up to get that next mirror in with the 2-mirror system in the ideal position. And you have the next optic, and you keep going down the chain until your system's fully aligned. Great. It takes time. It's not really an ideal process for complex prototypes. We have these added complexities of all of these mirrors have 6 degrees of freedom, plus the stop that we have to position, plus the housing we have to position. So we were looking at potentially 6 different holograms to build this. Some way of getting quarter frames of all of these adjusters to directly map the motions we wanted to make to be able to feed into actually how to process the system. It was daunting, and honestly, for a quick turn, low cost prototype, it was going to be extremely expensive. It was going to be about 1/3 of our budget to really properly metrology the system out. So we sat down and were like, we need to do this a better way. And really, when we were thinking about the way we wanted to do it was, well, why can't we just move all the mirrors at once? Just put them in, get it done, move them all at once. Well, first you've got to get them really close. We can do that with laser tracker. That's pretty good. Then you need to know really how to move them. How do you know what's good, right? This is a complex system. The topology of the alignment, it's all over the place. There's no one direct optimization path. You can't know to turn actuator 1 this far, actuator 7 this far, and the right combination. It's just too messy. You're going to land in all kinds of local minima.
Do you find that you need a global coordinate basis, just like you were doing in the simulation sense? Do you need to define one of the mirrors as maybe not the primary?
Absolutely. That was one of the biggest pieces there. It's like, well, we need a global coordinate frame in the system. You look really carefully, you can see some SMRs defining the entrance pupil aperture. There's some nests around there as well as at the top. So we know exactly where the center of our housing is, and we can define everything from that kind of center point axis definition on the housing that's there.
How do you pick that?
Chris, how do we pick it? We pick something, right?
Yeah, I think, I mean, we use actually the primary for a lot of our main reference, but we basically you need to pick one thing and then you can align everything to that. Yeah.
So we do make it a little easier on ourselves, and we just said, let's not move the primary. Okay, that got rid of 6 degrees of freedom. Great. We're still down to 20 degrees of freedom. We have to manage in the system to get this aligned to diffraction limit. So let's go with this idea. Let's try to move all of the mirrors at once. So laser tracker gets there. And how good does the laser tracker do? It does really well. First light, and literally this is our first light image. We did not try to put the interferometer through before this shot. 3.4 waves, peak to valley. We've got fringes. We don't see any aliasing. We are close, right? I mean, it's not good enough to sell it off, but we are close. You can definitely see the mid-spatial. This is pre-MRFing the mirrors. So this is a complex off-axis system. We need to get off-axis field points. We can select just a couple of field points to measure. Take a handful of measurements. Now we get a sense of our off-axis aberrations and our on-axis aberrations. And that gives us something that's there. And then the real brilliance was we went in and we calibrated each actuator. We set it up and we moved it, just a little bit. We took each one and moved it 1/8 of a turn. And did that for just far enough until the wavefront fell off. And said, okay, let's assume everything in this world is linear. It's probably a good assumption that over small motions, things are linear. They tend to be. Let's just see what that linear motion is, and we mapped each actuator to the system. Now, when we go and take a measurement, we can then feed it into what amounted to, and we didn't realize this till after the fact, it became a Monte Carlo machine learning solver. We can go and feed in those actuator motions, that linear motion, and just start firing solutions. If we move the actuators this much based on where we start, what would the expected output be? And you can run 1 billion simulations in about 5 minutes on a laptop. So we sit there, we honestly, the measurements take about 30 minutes to take. And the laptop generates something in 5 minutes for us to be ready to move. And so once we get that, we can start seeing there are features here, right? It's like, you don't want to be chasing the smallest wavefront. You don't want to be all the way on the left of the graph, that's getting lucky. You might not actually get there, right? We still can only move these actuators, right? We're turning these by hand. So I can I can come up with a motion and then say, okay, I need this actuator turned a 16th of a turn, right? There are no calibrated granular. It's take a wrench and turn it a 16th of a turn around the circle and, see where we're going. So we don't really chase the left. The philosophy we took was we want to improve by somewhere between half and 2/3 of where we're at right now. Don't want to go all the way. Don't go for broke. Go for better than 50% of where you want to be. And so we can look at the map and we can look at what amounts to the densities. This is a very common machine learning technique where you're looking for center of mass. And that gives us an idea of what we need to move and what's the most influential to move. You can see where it's well centered. That means probably, things like the secondary, the tilt of the secondary, it's not really going to do much to the system, right? Its center of mass is really, in the middle. But things like the decenter of the secondary, well, let's say it's about 20, and I don't remember what units that is. It's 20 off from the 0 point, which means we probably need to decenter that mirror down, the equivalent, I think that was 20 microns in the center. Similarly, the tilt, you can see the tertiary probably needs to be tilted up. You can see it probably needs some motion in z-axis on the secondary, and it gives us a general idea. Now we try to pick the 3 or 4 that are going to most influence the system. And that does take a little bit of guess and check in there to figure out which ones are going to be most influential at that given time. And then we iterate. We make those motions. Remember, it only takes us a couple of minutes to make those motions with the arc mounts. And then we remeasure and repeat. And, in the end, it takes, honestly, we can align the whole telescope from mirrors out to put in 5-ish hours. We've gotten it as good as 2 iterations. That was pretty lucky, but it's somewhere between 3 and 5 iterations of the system to bring it down from 3.4 waves to, well, right there. Fully built, it's around 0.036, 0.04 waves across the field of view. We hit pretty much every one of our specs except field of view in the system. And the performance is phenomenal.
The one thing you mentioned early on was like the 3D printing of this housing. Just like similar to like casting or even like a post-machining operation from that to get accurate,
Absolutely. That's one of the nice things about having the diamond turning machine in, is that we can take it, we can get 3D printed, and then send over the diamond turning machine and say, hey, cut all of our paths flat. Put it up on all of the same precision metrology we use to cut the mirrors and make sure everything's nice and square, it's stress-free, and that does help us bring everything together. Similarly, the pads on the mirrors that come with the diamond turning machine went up, so they're all very plain. That's in there. Great performance. I'm going to come back to this though. That field of view, that really bothered us. We were like, why is this so good and we don't have the field of view? And the answer is, annoyingly enough, boundary conditions. We miss this, and it galls me. Like, I see that mirror, that's all I can see. But if you look really carefully at the very edge, there's a couple of high points. If you look even more carefully, that blue, there's a ripple there, and it gets lost when you're looking at your computer screen there until you blow it up to the size of a room. We didn't notice until it got to diamond turning, and the computer code sent back to us what the toolpath shape was. And our diamond turning engineer, Dimitri, was like, there's this crazy ripple around the outside of the mirror, and the tool can't move in and out fast enough while it's moving. We're going to have to change the parameters. And we're like, well, what's going on? And it's that boundary problem. We hadn't pulled the ray grid far enough out when we did the prototype. We thought we had, and even there, because remember, it's a 3rd order spline fit, which meant that the control points were still slightly influencing it, even though it wasn't quite far enough out there to get rid of that. We've since gone back and actually reiterated on it to correct this problem. Now that we know it was there, we could build a tool to actually go in and detect this and make sure it doesn't happen again in future models. But it's a great lesson learned that says, man, it's a complex system, and things that you don't think are influencing or things you think you've controlled can still affect the performance. So it's a trade-off, right? I can get 0.04 waves across a massive field of view. It's a complex thing if you're not looking at those small details throughout. Of course, we gotta go take pictures, right? I mean, what's the point of building a prototype camera? We went, grabbed an off-the-shelf lens, off-the-shelf focal plane, threw it on. Again, did a little bit of guerrilla testing and took over a senior staff's office while he was out on vacation. And started imaging all of the fun stuff around the lab. You see Bedford Town Hall there, a couple miles away. Same water tower. It took us a while to find a good spot where we could image it. You can see different fields of view. We can swap lenses and get different resolutions, different sort of qualities, but you can see the same sort of features that are there with different F numbers and focal lengths. And of course, we're right next to the flight path of Hanscom, so targets of opportunity are always there, and it's really fun when we can actually land a plane and be able to pick off tail numbers as they're going by. So, wrapping up, Freeforms, they've come a long way in just a few years. They are getting really practical. They are really worthwhile if your system is worth supporting it, because you do see a lot of benefits. Now, not all systems support Freeforms. Not all systems need Freeforms. It's not something you should just throw at an optical system just because it's buzzy or it sounds like it'll improve it. They add complexity. They can add cost. It's not a panacea. But when you really need to push, especially off-axis systems to lower swap and higher performance, it's really, really hard to beat a Freeform in that system, either as all of the mirrors or even selectively used throughout the design itself. And I will stand by this, NURBS, they cannot be beat for performance. You can, on milder systems, you can get the same level of performance, but the more complex the system gets, you need better representations of the surface. And at least commercial code, there are not enough terms in commercial code, polynomial terms, to let you get to the surface shapes you want to be at. So having a way to represent the perfect surface, NURBS, essentially lets us jump all of that problem of going and custom adding an even more complex equation to the system. It's baked into the numerical solution of NURBS itself. So I would like to first, I want to make sure I definitely thank everybody who's been working on the Freeform project over the years, especially Chris, who's in the audience here. If you have any questions about optomechanics, Chris is the guy I go to. As well as Amanda Smith, obviously Michael Crisp, who really kicked off the effort here at the lab, as well as Paul Krostev, who did a lot of the design of the Phano code itself. So Michael architected the math, Common translated into something we can all use at the here at the facility. And a bunch of other people who participated in the arc mount design, in design of the application and the use and the concept of it, as well as our fabrication support team. You've been amazing helping us figure out how to take these shapes and turn them into real mirrors. And obviously Josh Brown is not here tonight, but I want to thank Josh because Josh was very much a part of this while he was here at the lab in developing a lot of this, especially some of the early developments of the math around the boundary condition problem. Josh was one of the first people to actually recognize that the boundary condition was a serious issue that we had to contend with. And sort of laid the groundwork for us to dive more into what's going on. So we'll take it back to questions. I went a little long, I'm sorry.
Two related to sort of final image quality, which is that far away to Bedford, you must have a lot of atmospheric fluctuations, and that's your final limit. And the second question is looking at how tightly your physical alignment is and everything. If this vision that all you have to do is turn it sideways, find a little different gravity for the whole space, you've got a realignment problem. So two things there.
It's the pointing angle of it, it's not so bad actually. It's a pretty stiff structure. The bigger issue is it's not thermalized. So when we took those images, we were constantly shifting focus in the system to try and keep it in. It was a relatively hot day when we took the pictures, so you notice the image isn't quite as good. The MTF of that lens it's an off-the-shelf lens from Avatar. Its MTF is not diffraction limited, right? It's degraded. So there's definitely things compounding the problems that are there for grabbing those imagery. When we brought it off the roof, it had about 10 waves of power on it when we dropped it back on the bench. Mind you, we sat there and watched the power literally just come back out to diffraction limited sitting on the bench. And this was after we'd taken it, dropped it on a cart, wheeled it halfway across the MIT facility, hauled it up on top of the roof, over the roof bars. This was picking up, dropping it, moving it all around, and it still came back to diffraction limited alignment. Those arc mounts are fantastic. I cannot sing their praises enough. But at least changing its orientation, we haven't seen much variation, at least the way this, the stiffness of this structure was. We do notice torquing affects it, based on how we have the mirrors attached. It can torque the mirrors a little bit.
So have you put at high altitude?
Not yet. It's just been ground tested so far. But we'd love to. We'd love to find somebody who wants to go put it on everything.
So, you know, going we'll have the best resolution optics, and you might be able to get away with something that doesn't have to perform well. Could this these new people be used to just reduce the number of elements instead of just making that latest greatest American aperture, make something that has less number of elements with lighter waves and approach that problem? Do you see any problems with that?
No, and that's nice. It's kind of a 5-tiered thing you can optimize, right? You can chase swap, you can chase field of view, you can chase entrance pupil, you can chase, resolution of focal length, whatever. These parameters are open to adjustment. When you go to, instead of Leo, V-Leo, right? You want to get closer. You have this disadvantage of, yeah, you don't need as big an aperture, but now you need a bigger field of view, right? Because you've gotten closer, so now your field of view, at least your ground swath that you're covering, has gotten smaller. So now you've got to, fine, it's the aperture field of view product we're talking about here. You're trading one for the other. So you can open up the field of view without loss of performance and still see the same spot on the ground. Also, you can target shrinking down the system. So you don't need a longer telescope. And we've got concepts for this that show that it can be about half the size in some cases of the equivalent performance.
So can you lower orbit and get into like atomic oxygen? Do these new surfaces present any challenges in terms of sustaining this kind of chemistries?
I mean, aluminum's a messy thing to work with in space. You have to be very thermally controlled to make it behave itself. So, worrying about activation of that sort of stuff, problem, because we chose aluminum, it's easy to prototype. We can diamond turn it, we can turn it around, we can show something. This was a 12 to 18 month project from concept to, us up on the roof. If we were to fly it, you'd want to be looking at, potentially better materials thermally. And that means, also being able to look at things like glass or, certain ceramics that wouldn't react in the same way to atomic oxygen.
An anti-reflective coatings, would you anticipate that they would way easier because the surface is much more contoured than?
No, we've seen none of that, at least with our systems.
Does the lab have the ability or interested in like commercializing this, or are there other software out there that's?
We are absolutely interested. The Technology Ventures Office would love to find a way to commercialize, the or at least find a way to have sponsors or vendors, partnering with our sponsors, sponsors being the US government, to be able to take out, access and utilize the capabilities, because clearly it's a better performing design when you use the tool properly. Downside, it's a homebrew tool. So there are quirks that we have learned to live with using this tool because it is homebrew and you understand the fussy nature of your own tool that it may not exactly be the most palatable to a commercial space that's out there. So there are some trades, but absolutely the lab would love to find a way to get it licensed.
Is there anybody else out there with the product or?
Not at the moment. Not.
the NES-Optica group? The Freeform group,
Yep.
do you interact with anyone?
So we do not here at we've talked about it from time to time. It's not a, consortium that we've opted to participate with, at the moment.
Because they have a lot of industrial programs.
Also for machine learning and return to the tool. Or as a substitute. Maybe it is getting this initial design of the last file.
So the machine learning, at least we've gone through right now, is more on the alignment side, finding ways of adapting. Well, essentially this manual process is us, we've looked at it after the fact, we're like, well, can we make this in a neural network? And we realized we manually built a neural network through their process. So it's definitely, the alignment stuff we can look at iterating into the sort of, neural network space. The optimization code for Phano is unique compared to what legacy commercial codes use. So it doesn't necessarily work in that same sort of way. So us figuring out how to translate that to anything other than the numerical method it uses, it's not really a route we've been able to go down so far.
James, can you speak to the algorithm? The optimization algorithm?
I can't. That's a different discussion.
That's the, what about wavelength? You have to, care about sampling the wavelength more than you would in the.
When you do refractive systems that have a fair amount of dispersion, it can impact it. A lot of that still gets made up with oversampling your pupil and oversampling your field. But there are cases where if your optimization in the refractives does move, red and blue far enough apart, you will need to have some level of wavelength optimization. It's built into the code. So you can actually modify the weights and the wavelengths in there. Michael was particularly interested in developing spectrometers, right? His name's against the author, Chris spectrometers. So he's always thinking about, can I use this for spectrometers? So a lot of the code was built in for some of his, pet projects that are in there.
Great. Well, we'll get picked out sooner or later. So I'm sure you're happy to answer questions offline, but let's thank him again.
Your alignment technique